think what I want to do is I want to start with this right here. And I want to start with the basic circuit, which is a coil and a trigger coil. They're wound together. So that means two wires are wound together.
That's like on the piece on the table, right?
Yes, yes. The coils are wound together, and then over there it's wound together.
Okay.
So anyway, what you basically have, you have a battery, and you're coming in the top of the coil. And when the magnets rotate, this is actually switches on and pulls the transistor to ground, which energizes this coil right here. And originally this pushed, but what we found out later on was that you want the motor to sort of re-gauge itself in so that you don't burn any energy in the circuit. So if you arrange this so it's in a traction mode, where it's attracting when it fires, then the energy is far less in this device down here in the transistor. All right, now the output, when this switches up and down in the basic motor, it's generating what we call a spike or a radiant pulse type energy, which is a spike. And basically what we want it to look like when you look at it with a scope is like that.
Okay.
And this, of course, would be the battery level, and this is the output from the coil when it flips the opposite direction. And what the idea is you capture this pulse with this diode, and you send it to the secondary battery. So you're storing everything that you're wasting in the motor. Nothing's being wasted. Now here in this depiction, I've shown you that you want the top of the coil so that when you look at the windings, they're counterclockwise. So you want them to be counterclockwise. And that will put this motor in a traction, because if you wind it the other direction, it's going to be in repulsion.
Okay, so question, on the bigger circle there, it looks like you've got the winding in clockwise.
Here?
No, on the bigger circle there, that one.
Well, the wheel is going...
Oh, that's the way the wheel turns.
Yeah,
okay.
the wheel.
Okay.
But the wheel can go any direction, Pat.
Okay.
So it really doesn't make any difference what direction it's going. So it will start in any direction with it. But we would like it to be, for all the efficiency of it, we would like it to be in a traction mode, because then we're using what Tom Bearden talked about, re-gauging, where we're re-gauging the electromagnetics in the circuit. So we're actually pulling the motor in for free. Mm-hmm. We don't want to burn energy pulling it in or pushing it out. Okay, when you push it out, you're going to burn energy because it's a push. You want it to come in for nothing. Of course, in the re-gauging type motor, this type system, remember when it's going in, it's being attracted in, that you only have half this pole piece that it can attract into. So I'm going to put it here so you can see that. If this is the pole piece, you only have half this pole. So the magnet can only be pulled in to that half. In other words, it cannot go all the way past the half line, all right? So therefore, all you're doing is attracting it in, energizing the transistor, capturing the pulse, which is this, which is a high voltage, and you're putting it back to the secondary battery. So everything that you're wasting from this battery and you're wasting over here, you're catching over here and putting back in this battery. And so as this battery goes down, this battery goes up. And what you're hoping for is you get 2 or 3 batteries here for the one battery that you depleted. Okay, now, later on, it was found out that you could parallel these devices on each coil. You could multiple wind these coils all together at one time, twist them all together. And then you could capture more by adding more stages, and that's why I've drawn this down here. It shows you 2 more stages, right? And then it was found out that if you isolate these bases with a resistor, that they can all share the same currents all the way down the line, no matter how many you have. And we'll go into that a little bit. But anyway, I want you to fully understand how this motor operates. So this motor is operating when you give it a spin. It energizes this. It becomes an electromagnetic generator. And the trigger coil picks that up and puts a signal to the base. And you must have some resistance in here, because if you don't have a resistance in here, you're going to overheat this device. You have to limit the amount of current into the base circuit. Because remember, if you really look at this, this is nothing more than an inverted amplifier. So any little small signal you put here is amplified here. And then this diode is to protect the base. And so we put that in there to protect the base, so that when it goes the opposite direction, it just takes a signal and puts it to ground. All right? So the idea is to get the motor to pulse itself around. So you give it a turn, it generates a pulse. And the 2 pulses, you're going to see a little miniature pulse on the base that sort of looks like that. Looks just like this. You're going to find that signal here and this signal here with reference to ground. So if your scope is grounded here and you're looking here, you're going to see this signal. If you flip the scope, you are going to see that signal. So once again...
What do you mean if you flip the scope?
Well, if you flip the scope probes and you put ground here
oh, okay.
and the positive of the scope here, you're going to see the opposite signal.
Yeah, okay.
Which is what it's actually doing. Because it's when this turns on, this transistor is pulling to ground. Mm-hmm. And energizing the coil. And when it switches off, the coil's reversing. It's reversing, and you're seeing this pulse, this spike right here. All right? So the main thing to remember about the simplified SG motor is to make it just like I tell you. You do it this way the very first time. Do not alter anything until you get this to run. Once you get this running, you can make all the changes you want to your heart's content. And then you'll find out the do's and don'ts of this circuit. In other words, you don't want to take this resistor down too low, because then heat appears here at the transistor. So we want to kind of keep it where it's going to start the first time, so you can get an understanding of the circuit and how it's capturing its energy to the secondary battery. Now, you'll see the spike here, which will be this. You'll see this signal right here. But on this side of the battery, you may not see that. You'll just see the higher voltage.
So wait a minute, how are you going to see that? Because you've got a little monitor on it.
Yeah, you put the scope here on the battery.
Okay.
And then by turning the gain of the scope up, you're going to see these little spikes that are appearing, that are high voltage spikes, and that's actually getting into the battery to change, to make the, to charge the battery.
When you say high voltage, John, what sort of are we talking about?
About 300 volts here.
Okay.
So about a level from here to here is about 300 volts.
Okay.
depending on how you wind the coil, how many turns you have on this coil. I suggest when you make a basic motor, you start out with 600, 700, or 800 turns on this. And remember, both wires, one real small wire and one real big wire. So nothing more than a number 20 wire on this side of the circuit, and nothing less than a number 23 wire on this side of the circuit.
Okay.
So if we put this here so you can see that. Number 23 wire.
Okay.
And number 20 on this side wire. And the total turns, nothing less than, I would say, than 700 to 800 turns. Okay?
Okay.
You want to have some induction when you start. You just don't want to put 50 turns on here and expect this thing to go, because to make it go, if you put 50 turns on here, you would you need to spin this wheel pretty quickly
Okay.
for it to generate this pulse on the base. So you want this, you want a lot of turns so that you can give the wheel relatively a small turn and it'll start going.
So basically this is all in a harmonizing...
Yes, the original concept of this motor started with Tom Bearden in I think it was electromagnetics for vectors. I think it was electromagnetics for, where he talked about a simple free energy motor. So this is where this basic concept started from. It was so hard to make the motor that Tom had talked about in that book, because you didn't know what the terms were when you were doing it. So what I did was, over the years, by trial and error and calculations on the number of turns and things like that, figured out a ratio that would do the same thing that Tom Bearden was talking about. And I knew that if I could get rid of the DC motor that was in his original and have something that would turn itself. So that's why we did it this way, because it generates its own energy to fire this transistor. So this half of the coil basically is not really doing anything except for an electromagnetic pickup.
So John, did Tom come up with the original concept, or did you?
No, Tom came up with what he called the simple free energy motor, and that was in, I think, Vectors 4, electromagnetic, yeah. And so I built that and ran that motor in the Silmar lab for a year.
Yeah.
Yeah, because Tom came out and visited, John Ratzloff came out and visited, and they always saw that motor running. In fact, John Ratzloff didn't believe it, so he locked it up in the lab. I gave him the keys to the shop, and I walked away.
Yeah.
I said, "Here, I'm not even going to be around. You're the guy here." So he locked it up, and he came back the next day, and it was still running and still charging the battery. But the problem was that with Tom's concept, is it used brushes, and it used a DC motor, which wasted a lot of power, which was, say, 40% or so. Now, we're not saying that was all bad. What we're saying is, why would you want to do that? Why would you want to run a DC motor and then have it turn a generator and have it switch back and forth with carbon brushes, where you'd have to replace something? Where this was much more convenient once it was analyzed what that thing was doing. This was much more convenient to do. And so what I did with this was a little girl came to me by the name of Shawnee Bauman, And she said, I got to do a junior high school project or grade school project, whatever it was. And they gave her this little matchbook motor to make, which was you wind it around a paper clip, hook it to a battery, and you're lucky if you can get the thing to go. And I said, come on, let's here, why don't you build this motor? I'll tell you what to do and you build it. And she did that. I think she won 4 awards. And then never could participate again. They came to her and said, you can't participate in the science fair anymore. And then nobody ever knows after that what happened to Shawnee Bauman. But once again, I'm going to tell everybody, do not change this. Make it just like you see it if you are learning, if you're experimenting with the SG. Don't change anything, because if you change it thinking that you know maybe a little bit better what to do here, it may not work for you. You may try to spin this and everything just burns up. So do it exactly like I'm telling you right here if you're a newbie in this. Don't go to the advanced stages until you learn all about this and you fully understand how it's getting the energy, how it's putting the energy back to the battery. And you're going to have to watch how this operates, because you're going to be watching this battery go downward okay? You're going to be watching, now I've drawn it backwards, and you're going to be watching this battery. What you want the thing to do is come like this. So you only want to burn this much energy from here to here to charge this battery. And that's what the concept is. So if you only burn that much energy and the battery's not depleted, you could have had 2 or 3 batteries on there and only burn that much energy to charge 2 of these batteries. So if there was another battery drawn right here, and it was paralleled with this battery should be able to charge 5 of these batteries on the back before this battery is depleted to 10.5, which is the lowest voltage this battery would ever go. So let's go over this one more time. This works because you give this a push, it charges this iron pole. That iron pole, then the magnetism is turned into an electrical pulse. The electrical pulse then turns this transistor on, which energizes this coil, and the next magnet's sucked in. When this transistor goes off, the pulse, because of the electromagnetism in the coil, the pulse is captured by this diode and sent to the battery, which is a high voltage, around 300 volts if your coil has enough turns on it. Depending on the amount of turns that you put is how high this pulse is going to be. So you don't want too few of turns, you want a lot of turns, because you want a high potential. Now, let's go back to Tom's analogy so you understand it. Okay? Ions are big. And to charge the battery, you got to move those ions. So you're moving the ions in this direction. So to make them move a little bit faster, all the electrons are building up around the outside of the ions, like this. And that's pushing it to this plate in charge. Then the ions are moving the other direction to this plate over here. I'm running out of room, sort of, but I'm going to do it anyway. So during charge, you want to build up this high potential on these ions to push them because they're going to move very slowly. They're big. So they're moving to the next plate to charge this battery. And during discharge, there's nothing building up on them and they're moving in this direction and depleting the battery. So that's why 2 batteries. This battery, the ions are trying to go this way, and in this battery, the ions are going that way. So, you understand what I'm saying there, Pat?
Yeah.
In other words, you're building up this high voltage electrical charge on these, and they want to move a little bit faster to that plate.
Okay.
So, and at the same time, if this battery has been sulfated, in other words, unusable, where you can barely get a charge in it, this is very good for it because this is actually breaking, this high voltage pulse here is actually breaking the sulfation off the plates. And so when you look at the plate, we can just look at the plate like this. This is all sulfation that's built up. And this sulfation will not allow the electrons and the ions to move. In other words, it's like an insulator in here. So what you're doing when you use this high voltage pulse is you're like cracking these and the sulfation's falling off.
Yeah.
And it's falling in the bottom of the battery. So it's good if you have a sulfated battery and you use this type of system to desulfate it. It's good to wash the battery out then and then refill it with acid.
How would you wash it out?
You would dump it out in a pan, and what's going to come out in that pan is going to be everything that is accumulated in the battery on the bottom. You're going to shake that battery up, and after your charge with this, and after you do that a couple of times and you've gotten all this sulfation out, you have a good battery. You have a battery that's usable, you can use for things. You know, so basically I want everybody to understand, and that's why I'm going over this. Do not change the circuit. Do it exactly like you see it here. And this will operate the very first time and show you what the theory is on how to recharge the battery with a secondary battery.
So where are we going now, John?
Well, we're in the second stage of the SG, but now it turns out to be not a schoolgirl anymore. Turns out to be an SSG.
And that stands for Simplified Schoolgirl Motor?
Yeah, except advanced.
Simplified but advanced? Okay.
Well, much advanced, because now what's going on here is we're using the same set of magnets. And we're also, again, I'm going to point out to you that we're in the attraction mode, so in the regaging mode, so that it regages to the next cycle. All right, except for one thing here. We're still using the same trigger coil right here, but this time you notice that all these coils are multiple on the same coil, so they're all wound together on the same coil all at one time. Number 20, I'm going to put it down here again. These would be all number 20 wires, and this would be a number 23 wire.
Okay.
So these basically could be all the same color, red, and this one could be green or blue or clear, whatever color you wanted to determine, you know, what the trigger portion of the unit is. And now if you notice this...
Wait, what do you mean? What does the color have to do with...
Color has nothing to do with anything.
It's just a color coding on the wire, is it?
Yeah, just so you know what the trigger wire is.
Which one the trigger one is.
Yeah.
I see, okay.
But I mean, you should be able to figure that out too, because a number 20 wire is bigger and a number 23 wire is smaller. But I have seen in situations where people have reversed these wires around. and then couldn't figure out why nothing's working.
Okay.
So, what I want you to notice here right away is now there are 4 coils in here and 1 trigger wire, so that's 5 coils together. Notice each one of these coils has its own diode.
Right.
That means that these spikes are being generated very quickly, sort of like that. And that means that the base signal is going to follow this signal, but much smaller level, as we covered earlier with the schoolgirl motor. So remember, that's you're going to see this signal with the scope probe grounded correctly, using its ground tab and then putting the probe on the coil here where the diode is. This is the signal that you're going to see.
So what's the added benefit to doing it like this?
All right. Okay. By doing it this way, we're generating much more energy. We're able to capture much more of these high voltage pulses, which means that we're putting much more to the second battery when we capture them.
Okay, yeah.
Because they're all going up together and they're all coming down together and they're reversing, and then you're capturing this energy. So you're not wasting any energy here. And then once again, this is self-powering itself around to generate the signal by the transistors turning on and off. So if you look down here, each one is independent from the other, see?
Yeah.
There's a coil here, and there's a base resistor here. And see, it's just coming in on where they're all sharing these base currents. And then you can tune it by adding a 5 to 12 ohm resistor here, and then you adjust it for the best speed possible. Once again, we want this in a traction mode, because we don't want to generate heat here. We don't want to push this wheel around. We want to pull it in. In other words, we want it to suck itself in, and then this is going to turn off, and it's going to go past that, and it's going to suck the next one in. Meanwhile, generating the energy on these bases. So the signal down on these bases are going to look sort of similar to this, but much smaller. So you're going to see this on the base. If you reverse the probes, you're going to see, sort of signals like this.
Yeah.
Because now you can see the transistor pull down. Remember, these transistors are pulling to ground.
So what are all those numbers on the transistor?
Oh, the 2N3055 is the device number. So that's a 2N3055, 1N4007s for rectifiers, 470 ohms for the bases.
Okay.
And once again, I want you to build it identically as I have drawn it here. Get it to work. Watch what it's doing here. Watch how it's charging the battery. And you'll see that it's charging the battery at a faster rate than what the schoolgirl motor was doing, because this is more advanced. This is more like for an advanced type student that's doing this. So once you understand the working principle of this, then you can make the changes that you want. You can experiment by changing these resistors. You'll notice then this frequency is going to change, because as you change this resistance, this frequency will change.
Yeah, so right now they're all, the numbers at the bottom are all IN4007.
Yeah, all the diodes are identically the same. So that's what's pointed out here.
And the resistors are all 470 ohms.
Yeah, they're all 470 ohms.
Okay.
And that allows each one of these bases to get the same amount of trigger signal. So they're sharing the currents coming
I
through the
just couldn't
coil.
read the numbers very well. Did you get a photo of that?
Yeah.
Yeah, I'll put the resistors are 470 ohms.
Okay.
And that these are all 470 ohms. The transistors, which are Q1 through Q4, are 2N3055. That's a common transistor that you can get, say, at Radio Shack or any parts store. They'll always have that transistor.
Okay.
So that's why I've chosen it for this drawing. The diodes are common, so they're 1N4007s.
Okay.
That means that this is a 700 volt part.
Okay.
This 7. So if this was an N4001, it's a 100 volt part. You want to be above 100 volts because this is going to generate a little bit more. This is going to generate, if this is wound with the correct number of turns, which is now going to be between 130 feet and 500 feet.
Collectively, all those together.
Yes,
Yeah.
collectively all together. This is going to be up at about 400 volts. So see, the potential's increasing here.
Yeah.
The potential's increasing again, which means that each one of these diodes is seeing a 400 volt spike, right? And they're adding together, not adding to the point to where 400 plus 400 plus 400, no. They're summing together to create that 400 volt spike
Okay.
at a little bit more current than what normally one diode would do. So let's say each one was doing a quarter of an amp. Let's just say it was, which it's not going to do. Then you'd have 1 amp of power there. All right? So basically what I want to say to you is that this now is much more advanced towards the free energy motor that Tom Bearden was talking about in, what was it, Tony? It was electro...
Vectors and mechanisms clarified,
Yeah.
part 4.
Yeah, and they can find that on the Tom Bearden website, right? That motor. And that's what started all this. Again, I'm going to point out.
Towards a new electromagnetics.
Yeah, towards the new electromagnetics.
Yeah.
And part 4.
Part 4.
Yeah. And so once again, we have the primary battery. We want to look at the same curves. We want to, as this battery goes downward, we want the charged battery. So we're going to look at a curve. That's, I'm going to get down here. Is it okay?
Yeah.
We want to look at a curve that's basically the battery starting out here and is going like this. And the charge is going like that. So see, with this type machine here, multiple batteries are no problem. You can have another battery. So both batteries are basically following the same charge curve, like this, from the one battery. And you have 4 devices, so you could put 4 batteries. You know, it's not a problem to do that. You want to deplete this battery and then get 4 charged batteries or 2 charged batteries for this one battery. Now, the only difference with this type of machine is these 2 forms of electricity are completely different. This is a normal, what you call normal, what we've taught in school. You're depleting this battery in the normal electromagnetics, right? And on the other hand, you're charging this battery with an electromagnetics that's talked about high potential. In other words, like almost like static electricity, but not quite. So the rectifiers once again are converting this spike to the high potential and placing that high potential on the battery.
So that's not radiant energy, right?
Yeah, it's radiant when you're dealing with fluorescent lights and you're dealing with, static discharges from the atmosphere and stuff like that, and you're capturing spikes. That's considered radiant. I mean, you can look it up. It's defined in those terms. Radiant. Some people want to call it etheric energy. I don't like the term etheric. I like the term radiant energy. That's more towards Tesla's end, the radiant part.
Mm-hmm. Is that the same as negative energy?
Yes.
Yeah.
Because what you're doing is you're actually taking this little spike, this little charge of energy, that's a good way to look at it. There isn't very much current in here because it's not very wide. What it is it's a high potential all at once. Bang! That's what is forcing these ions, the charges building up by that little spike. No current, basically. Just a high voltage. And then that's forcing the ions to move. Of course, during discharge on this battery, the ions are going this way. This one's discharging, this one's charging. And I always liked to use 2 batteries in the system. I'm going to tell you why. Because one storage battery on the simple free energy motor, unless the phases are absolutely correct and towards a new electromagnetics, unless those phases are absolutely correct on the machine that's on Tom's website, you will not get the battery to charge. You will lose. So timing is very important, too important to goof around with something like that, unless you have a lot of experience in this, in how to trick the one wave and then the other wave. If you can't do that, because what you're actually doing is you must be able to charge the capacitor towards electromagnetics in that machine. You must be able to charge that capacitor instantaneously. With this type of spike, the bigger the capacitor is, the longer it takes to charge that capacitor. Because you can figure that if this is the capacitor, you're going to be charging it like this, up to full. Then you're going to come along with that brush again and have to switch this. You're going to have to take that capacitor and discharge it to put it over here to this battery. And this is all going to lead into the next thing. But point is that with very small spikes like this that don't have very much current in them, it's going to take you a while to charge 60,000 microfarads. It's going to take you a while to do it, especially if this thing is not developing and it's all tuned wrong, right? It's going to take you a long time to get this charged. So what we want to do when we're dealing with the SSG motor or any of the advanced motors is we want to know exactly how this motor operates, because there's a great understanding that comes from that on how to charge batteries, which is in the future now, is solar power and batteries and things like that. We want to know how to get this battery charged if we only had a small amount here. In other words, if we only had a small battery, and we want to know how to get as much as we can out of this system to get the 2 batteries charged or the 3 batteries charged. Now, some people, it's been reported to me, cannot do it. They just can't do it. No matter what you tell them, they can't do it. There's others that can get 4 or 5 or 6 batteries to charge with no problem at all. But like I've always said, when you're into these type mechanisms, this is a brand new field. This isn't a field that's taught in electrical engineering. So once again, you're dealing with a pulse motor. You're capturing the wasted energy in the coil itself from the electromagnetic pulses. You're rectifying that to a high voltage, and then you're sending it to this battery. And what is this battery doing? It's being charged by these pulses. Energy is being derived to rotate the motor around too. If you really look at the signals, what's actually spinning the motor around and around and around is this high potential spike. So you're not only generating it in the base circuit, which is the trigger coil, which they call trigger. So you got a trigger, I'll just put a T here. And that's your trigger coil. This is generating this small impulse, you know, that looks sort of like that. And that's what's telling this transistor to turn off and on. And so they're all doing it at the exact same time. So they're all going up and they're all coming down. And if one of these was to go bad, say shorted between the base and the emitter, they all cease to function. You will not get them to function, so your motor's not going to run. And if they short from collector to emitter, what's going to happen is this motor's going to lock in position, and no matter what you do with it, you're not going to be able to turn it on until you find which device is actually shorted. And I've seen that. And I see that happen when either the resistance on the base is incorrect, or this diode isn't big enough to capture, to handle the spike, or there's something that occurs that you're not really expecting, where it just puts this spike right to the base automatically and nothing's protected. And then it just shorts that device. So what I'm telling everybody is you build it exactly like I've showed you here. Just study this.
I have a question,
Yeah.
John. How does it flow around that? Which way does it flow around all that diagram? Does it go 2 separate ways?
Here, come.
Well, you're talking about this spins around, right?
Yes, this is going to spin whatever direction you want. In this case, we're going to spin it that direction.
And it gives a trigger to this?
When the magnet, here, can you catch this, Tony?
Yeah.
All right. So we have a coil that's sitting here, and it's got a piece of iron in it, right? And that iron, this coil is inside this iron, right? And there's nothing going on right now. There's nothing that's generated. There's nothing that can be caught except ambient, whatever. This is an iron pole, right? So when the magnet starts to come across this, it sort of charges up this iron.
Right.
When the magnet leaves, it breaks the iron, and you get this pulse.
Right.
See? So this magnet goes past,
Right.
and then the iron discharges and creates the magnetism. In other words, right now it's a magnet when it's charged.
Okay.
So this field is, you know, like this around this coil.
Okay, but on this, when it hits the coil, which is here, right?
No, it hits the iron
It
pole.
hits the iron, right?
Right.
Does it go this way or does it go this way? It goes this way.
No,
right?
this charges up. In other words, it becomes a magnet.
Okay.
When the magnet leaves, it's not a magnet any longer, it discharges.
But this is a trigger.
Right,
Yeah,
so what it does is induce this current into this coil.
Uh-huh.
And that's the trigger. And then this turns this on, which then in turn turns this coil on,
Okay.
which causes the next magnet to be attracted into it.
Okay. So this is a separate thing down here than this.
Yes, this
Yeah.
is all part of, this is the coil,
Right.
this is part of the regeneration system,
Okay.
and this is part of the electronic triggering
Okay.
that tells this thing to keep going.
Okay.
So do you see what I'm saying? Do you understand that? In other words, you have to charge the iron.
I'm trying to see little arrows going around the circuit.
Well, maybe we can cut over here for a minute. All right, Pat, here it is.
Mm-hmm.
There's nothing going on in this.
Right.
See, it's magnetically locked there. See
Right.
it? See that? Okay, but the minute I go like this, and I cause that magnet to come across the coil, the minute I get it to where it electromagnetically
It
starts to generate
Right.
the this trigger signal here,
Mm-hmm.
then the motor runs.
Okay.
And it continues to run.
Okay.
In this motor's case, there's no recharging of any battery because it's just to demonstrate the principle of induction, what you're talking about right here. This is the same way an easy way to put it is like your lawnmower works. When you give that cord a pull, it's firing the magneto because of the magnets.
Okay.
And then the spark's generated, and that's igniting the gasoline, and the engine just takes off and runs. So basically that's what's happening there. It's generating a spark to these bases, right? And that spark in turn is turning this device on, and that's turning this coil on, which is sucking it in the next time. So it continues to run.
Okay. All right.
And that's basically how this whole system operates. So in a way, it self-generates. It doesn't use any power from the battery to generate that signal. So
Yeah, I think I was confused because I was seeing the power coming from here
going into
and then
these
going
coils.
back over here, and I was trying to see where it was going. Yeah.
Well, it only goes back over here
Yeah.
as soon as the spike is generated and you can
Right.
capture this.
Yeah.
Then each one of these is capturing that amount of energy, right? And sending it back to the second battery. Like I said earlier, I like two batteries because I can watch what this one's doing
Yeah.
and I can make adjustments to this one to burn very little power, right?
Mm-hmm.
While gaining the most voltage I can get here to charge this battery.
Right.
And see, it's not a current type thing here. There's not amperage involved here.
Okay.
There's microcurrents,
Yeah.
you know, milliamperes involved in this spike. Because it's not wide. It's a very narrow spike. So there's not much current here that can be delivered. However, if this was wide, like that, this could be a half amp, where this could be 1 milliamp.
Okay.
But that's, see, the idea is to get these ions to move themselves for no current.
Yeah.
So that's what this is all about. This is all about on how do we alter this battery to recharge itself
Yeah. Okay.
without using a lot of current in the system. So that's one thing to think about.
Yeah.
You know, most people are saying, okay, Yeah, but this is not going to run my house. No, it's not going to run your house. This wasn't developed to run your house. This was developed so that everybody could understand what the theory was on how to recharge a battery. How do you recharge this battery for very little current when a storage battery wants to have current to charge it?
Yeah. Yeah, okay.
No, do you understand a little bit?
Yeah.
You're going to understand it even more.
I was trying to see little bitty creatures crawling around.
No.
Going, you know.
No, all this thing is doing,
This
see,
is an instantaneous thing that happens, right?
yeah.
Yeah. So,
Yeah, it's like a magneto.
yeah, I was thinking, couldn't we have little arrows showing which way it's going? But it doesn't go like that. It happens in pulses.
Right, it happens in pulses, see?
Yeah.
Look,
Yeah.
watch.
Right. And it just keeps going.
See, the problem with the simple free energy motor, which was this here, the problem with this thing is here is, you see, you got a DC series motor, and it's turning an energizer, which is like a generator, right? Then you have a controller, right, that makes these switches go back and forth. So in one mode, it's turning the generator and dumping it to the battery, see? Right here, Tom's got it drawn. Battery powered to motor, see? To terminal. In other words, generator. So motors on, motors off, generators on, motors on, generators on. The mechanism is a tough one, Pat, because not anybody could build that. And they haven't built it.
Well, once it occurred to me that this wasn't a question of little things walking down the street. It was just a...
Well, it is a question of little things walking down the street. These little things got to walk down the street here to turn it on.
Right.
The terminology is the confusing fact. The machine's another problem because when you start confusing all the terms and you don't understand what you're dealing with, you don't advance.
Yeah. And already we've had, is it a radiant or is it a,
Yes.
you know?
Well, you know, one thing Tom does have on his website is a phenomenal glossary of terms.
Yeah.
It has 1,000 different definitions.
Right, but who's reading it?
Well, the webmaster.
Returning to this drawing. We're not quite done with this yet because there has to be more understanding to this, because typically this system is nothing more than a simplified form of towards a new electromagnetics for the simple free energy motor. All right? So, what is it that we want to accomplish with the motor that recharges a battery? So, I'm going to flip this. This is the concept. Something that's close to a generator, but it's not a generator. It's called an energizer. So, okay. Now, the next thing you're going to say to me is, what is an energizer? An energizer is a mechanism that can generate energy without any drag to this motor. So, pulley, belt. So now, when we turn this DC motor on, it turns the energizer. And the energizer is basically what is known in simple terms as a flux gate, or something that works on the principle the more impedance is applied to it, the less resistance there is in turning this. Now, so the next thing is if we have a battery here that's 12 volts, and say we want to recharge this battery. So, if we build a switch and we have designated terminals, plus and minus, all right? So what the idea here would be is to build a control mechanism that where the battery we build a switch, and this switch is controlled by something that turns this switch off and on. So now we have a negative portion to the switch. We have a positive portion to the switch. And this then is applied to the motor. Now that's normal fashion. The motor is on. The motor is spinning. However, this switch must do a flip-flop thing. First it powers the motor, then it connects the energizer back to the battery. So, what's the signal? The signal is the switch turns the motor on and then turns the motor off. So it goes on, off. Now, when this goes off, what's in line here is the energizer. So this is the motor, M, and this is the energizer signal. So what's happening here, to get this thing to run very smoothly, you would have to have a weight out here, or mass.
Like a flywheel.
Flywheel, right,
Okay.
mass. Because you want to run past the dead cycle, right?
Okay.
And you want the energizer to put that power that you just took from here back to the battery. So what you would really be looking for is to recharge the single battery. But that doesn't always work well because batteries don't like to charge while they're discharging. So the most you can hope for with a system like this is an extended range. The real key point here is that when Tom talks about the simple free energy motor that powered itself, we read the words, right, Pat?
Yeah.
And those words were hooked in a Delphi River, zero Fadot.
Yeah, it was.
Yeah. So it's kind of hard to understand, okay, what's Tom talking about here? And why did John do what he did? All right? Something very important here. If John could build a motor that had the coil, which is nothing more than the SSG circuit, and the wheel with the magnets, why do I need this motor if I can rotate this by itself from a single pulse? So, here's the analogy. I don't need this energizer because in this circuit here, when this energizes from the battery, when you give it a spin, it generates its own signal to turn this transistor on. Then it takes power from this battery in a pulse. So once it generates that pulse, this mass is spinning without this DC motor, no brushes.
Okay.
So I don't need to apply continuous current to spin that motor up. You follow me? I can supply a pulse. I can supply this little bitty pulse that will turn this coil on, suck the magnets in.
Okay.
And here is the trick, is called the energizer. This guy right here, what's an energizer doing? See, it's all built into one in the SSG. You have the mass, which is this wheel. Mass. You have an electromagnetic pulse being generated from a free source, which is a permanent magnet. When this energizes this and breaks away, then you get this pulse. And that's what turns on this device, which is the transistor. When it turns on that device, there's another electromagnetic field that's generated for a small amount of time, and it pulls the next magnet in or pushes the next magnet out. Either way you can do it, attraction or repulsion. I suggest that when you're learning all about this, you do it in attraction mode because you want to burn the least amount of energy. Okay, what is the energizer generating? The energizer portion is when this whole system is disconnected from the motor.
Yeah.
So that means the motor's off, right? And what's the energizer portion then? It's what was left in this coil that flipped around the other direction, and that is this, a massless charge. This is a high voltage charge, and this high voltage charge has no current available to it because it's so small. So when Tom talks about Delphi waves, he's talking about this massless, this charge without current. And that is what's going to the secondary battery. Notice that the minus on this machine is returning up here to the positive. So it's completing the whole circuit.
Right.
Yeah. So this is why I do not do it this way, because I built it all
At that level, yeah.
in one machine to prove out the concept of a battery that recharges itself, except I isolated the batteries because I want to see it. I don't want to just go ahead and try to put this back and then build another set of switches that completely turn everything off. All right? Now there's only one other way around this so that you can see the battery in the front bounce up and down, bounce up and down. And that's if you put a capacitor here that you were charging. So now you have to hope that this charge can charge this capacitor fast enough to build it up to double the battery voltage, which would be 24 volts. And then when this contact comes over here, you're dumping this capacitor that's 24 volts against 12 volts. And this is staying at 12 volts because it can never go any lower than 12 volts. But there's another problem here. The next problem is when you're doing this way with contactors, you're generating arcs. And sooner or later that switch fails and the machine stops. It gets stuck in one position and that's it. So the idea was, from the simple free energy motor and towards the new electromagnetics 4, was to build a machine that represented this machine all in one machine. And that was the SG. So let's go back. And here's your massless charge.
Right.
Where's the energizer portion? It's when this shuts off, when this turns off, it's actually the coil is your energizer. Because this flips over and gives you this spike, and it's captured right here and sent to the secondary battery to watch the charge. So you have the whole machine without any contacts. Now, why did I use 2 batteries? Because I am interested in studying the charge. I want to see how this massless, currentless spike charges this battery. Once I understand how this charges this battery, it's easy to take the machine and make alterations to the machine. So, I'm hoping that you fully understand this. Do you have any questions about this, Pat? About, you had said something about something here.
Like I said, I was trying to see little creatures crawling along the wire.
Well, basically you could represent that. You could represent, you know, this current is flowing down this way to turn this on, and then the current is flowing, then this current's flowing down through the device, and then when this turns off, the current flows the other way, generating this spike, right, from the electromagnetic portion of it, which is actually a motor energizer. This is all built into one. So when we go back to this, we've built this whole machine in towards a new electromagnetics 4 into this machine, which is the SG, which is the same concept.
Right.
This is the energizer and the motor all combined into one, and this is the mechanism that's turning the motor by generating the pulse, by capturing this trigger signal. Anyway, I hope you understand the difference in concept, what exactly I was trying to do here when I built this machine, was to generate this Delphi wave, to study this wave, to recharge the battery here. What was it that was recharging the battery? What was happening inside the battery to do this? So, once again, it's the high voltage potential without current that forces the ions and the electrons to move at the same rate across to recharge the battery. So basically what you have here is a machine that is supplying a little electrical impulse to this coil to get a big gain out of in voltage to move this, the electrons and ions, to recharge the battery. So there's another way to do this, and it works very well. Once again, we have the SSG. And I'm going to point out again, you want the SSG in a traction mode. There's a reason for this. The reason is that you don't want to generate heat in the device. You want the motor to pull itself into the magnet, go past to generate this little signal, which is this spike again, this little spike, to turn this device on to energize the coil. And then it's pulled in again. All right, so let's go through this a little bit. Once again, I'm going to point out the coil this time, length of wire is 130 feet. So now we're shrinking the coil down a little bit, and we're making the magnets a little bit stronger, but we're not using neomagnets. Neomagnets are incorrect for this type of motor for the simple fact that you can't pull out of the lock. You have to generate more energy to do it. Now, yes, true, people say, well, I can space the wheel away from it. Fine, if that's what you want to do, but it's incorrect. You want to use a ferrite number 8 magnet. That's all you need to do this with. So you want to use a ceramic magnet. There's a reason. If something heats up with a neomagnet, you will lose the energy in the magnet, and therefore the motor will go slower and slower and slower and slower, and pretty soon you're not going to generate what you thought you were. Anyway, once again, we're generating our trigger pulse with this. Now this is much more advanced, this motor. We have one primary battery that we're using to still study the same situation in here. What we're doing with this is we are coming in here, and the radiant or the delphi waves or the massless current, which is this signal, is being charged in this capacitor right here. And we've selected a capacitance of 60,000 microfarads here. What we're doing is we're now making the machine charge a capacitor, but very simple. We are taking this massless current spike in voltage, and we're building up a charge in this capacitor. And when this charge reaches a certain level, there's a comparator here. And what that comparator does is it allows this capacitor to build up, and when the voltage divider on the comparator says that's the correct amount of voltage, it switches on and turns this FET on, which dumps this capacitor.
Was it FET?
Yeah, FET, F-E-T.
What does that stand for?
Field effect transistor.
Okay.
And you can see here what's going to happen. It's switched on the negative pole. Positive is always connected directly to this capacitor because the potential is built in the capacitor. And then all we do is switch the FET with the comparator to ground, and the battery recharges. And you can take it further than this, in that if you notice this drawing down here, I'm showing two diodes, one in this direction, one in this direction, because I want both cycles of the machine. And then the capacitor is going to charge faster, the comparator is going to go faster, and the charge is going to go much faster to this battery. So you can see how we've taken our simple free energy motor and built it all in one machine to do the same function without the switching of contacts, because everything is electrically switched here. And by the way, the comparator is nothing more than I've showed before. It looks like this with all the FETs and the indicator that shows when it discharges by the flash on the green light. So in the earlier DVD series, you will see this comparator running on the SG machine. So, what I want you to understand here is this is much more advanced, much more sophisticated to do, and requires a lot of work for you to build this comparator. And the important thing about the comparator is you don't want this comparator to stick on. You want this to actually discharge the capacitor, which is going to look basically like something like this. Which is a sawtooth signal. So that's the capacitor charging and discharging, and charging and discharging, and charging and discharging. So right now you're a little bit limited here in how fast you can charge this capacitor, because what we're actually moving the machine into is a full energizer that can generate energy. So a generator without drag on the wheel. In other words, we don't want to burn energy from the battery to generate energy to charge the battery. So what we're doing is we're taking this little bitty pulse, which is generated by the trigger. We're amplifying that pulse to look like that to get our 300 volts, or 400 volts in this case. And that pulse right there is what is charging the capacitor, because this part of the pulse is at the battery level. So therefore, that's not enough. This battery level is not enough if you put it here to do anything with the comparator to charge this battery. It would be that if you were just going to use this portion of it, you're just going to equalize these two batteries. You're not going to do anything more than that. So you haven't gained any charge. In fact, you've lost a little bit from this one to this one, and then this one back to this one. We don't want to do that. What we want to do is we want to turn this off and on and totally disconnect the machine from this current in this battery, from this battery. And we want to charge this cap, and when this cap reaches a certain level that's good to charge this battery, and that would be like double this battery. So
cap is a capacitor, right?
Yeah, that's this.
Okay.
This is the capacitor here, Pat.
Okay.
Okay, so there's 4 of them here.
Yeah.
They're 15,000 each, so that's 30,000, and 30,000 is 60,000 microfarads.
Okay.
That's quite a big capacitor.
Okay.
That's a lot of microfarads, and when you charge it up to double the battery voltage to maybe a little bit more than that, you're dumping a lot of joules of energy.
So that's that 60,000
Yeah.
MF you've got written down.
Yeah, right
Okay.
there. Right.
Okay.
Because it follows this thing exactly.
Okay.
In other words, it's a simplified drawing of it, but this basic machine is just sitting just like this, like you see it.
Okay.
The FETs are at this end, right? The comparator and the switching circuits are at this end, which is right here. And then there's an LED, which I did not draw in here because I didn't think it was necessary that I put an LED in here.
Right. Okay.
And then this is the capacitor. And then the diodes are over here at this end.
All right.
So, the other thing about this whole circuit is this capacitor is actually controlling the functioning of this circuit with the voltage at the same time. It's generating enough energy that it can run the comparator circuit, switch the FET, and discharge this to 1/2 the battery. In other words, from the double voltage, it can discharge it to 1/2. So the capacitor could never really go down below this battery voltage. So what you'll notice on the capacitor when this is happening is that the voltage keeps raising on the capacitor. In other words, keeps going higher and higher and higher and higher and higher as this charges up more and more and more and more. Well, in a way that's undesirable because you have no regulation whatsoever taking place here. So you're at the limit of you're monitoring this battery with a meter. When the battery reaches 15 volts, you're saying, okay, my battery is charged. And you should shut off the machine at that time. Because anything more than that, this battery would want to try to keep raising, although it will not do it. It would want to keep trying to go higher and higher and higher and higher and higher, and that's just boiling the battery away. It's useless after that. What you want to do is you want to maintain this with some kind of regulation system, which will be talked about later. But once again, I want to point out to you, this is a normal SSG. This could be multiple coils, 470 ohms again. The same 1N 4007 rectifier, same rectifier here. Coil at 130 feet, number 20 wire. Trigger coil, number 23. Same set of wires, all twisted together. And again, when you look at the top of the coil, you want to make sure that the top wire comes out counterclockwise. That puts the machine in a traction mode. Why do you want to run in a traction mode? Traction mode, then no heat is generated in this device down here. You can put your fingers on it. It's cool to the touch. That's where you want this device running at room temperature. You don't want this device so hot that you can't touch it, because then you're just losing power. So, once again, for the ones that understand what this circuit is with a comparator, to put the machine into generator mode, you would add this diode down here. And the reason I call that generator mode is because then you're starting to push a little bit more than what this is in current. And it's allowing this capacitor to charge much faster and this switch much faster, which means that then battery over here is gaining much faster as this one's going downward. So as this battery here is going downward at this rate, this battery is going upwards at that rate. So this would be around almost 16 volts. You don't want to take your battery much more over 16 volts.
So which one is going down? The primary battery is going down?
This is the primary,
right,
which is the bottom curve, which is actually
right,
should be, this is P1. And this is C1.
Okay.
So you want to use about, you see, you don't want to use more than half the energy in your battery to get this fully charged
So
up to 60 volts.
Going, yes.
So the bigger this capacitor is, and the more you can supply to this capacitor quickly without taking much energy from here, the faster this battery is going to charge up and you'll be done. And then the faster you can charge the next battery and the next battery. So again, this is to study. The reason I did this was, I want to see what's going on, how quickly a pulse charge battery. So basically when this thing turns, when it switches, this pulse is much bigger now this way, which means current. This means that now you're developing current in a pulse to charge the battery. And when you push current in pulses, things start to move a lot faster. This is the theoretical concept of a radiant charged battery. This is the concept of a pulse charged battery, which means that you're pushing a little bit. You can actually watch this. So if you had a meter in line with this line, you could actually watch the current pulses go to the charged side of the battery. This one would be going the opposite way. This one would be going this way. So now, if we think about this, isn't the simple free energy motor this? See? Motor on, generator off. Generator on, motor off. Motor on, generator off. Generator on, motor off. So, the idea is that you must get the phasing absolutely correct in this machine. If you were to have a DC motor like we pointed out earlier and an energizer, these two must be 180 degrees out from each other.
Right.
So basically this is an on, this is an on. So this is the motor, see, and it's off here. And it's off here,
Right.
okay? So motor comes on, capacitor charges, energizer, which is the comparator circuit along with all this mechanism. This is actually your energizer portion. And then it dumps this capacitor to this battery, which is on this on. See, motor's off, capacitor's on. So that's what you want. You want it in a traction mode again, because you don't want to generate any heat here. You basically want to pull the magnets in for free, is what you're doing here. And you want the primary battery going down at a rate, and you want the C1 charge rate going up very quickly because the pulse is high and has a lot of energy density in it. So now the pulse is getting bigger and bigger and bigger, wider by the timing on this. So you can make this a lot wider, and you could watch the current go further and further and further within limits of what this machine would charge it. You don't want to overdo it and you don't want to underdo it. You want to put it right in the middle. You don't want to change anything. You want to build it just like you see it there until you understand what the concept is. Then you can make changes with a comparator. You can do whatever you think is necessary. And you find it out your way what works the best to charge this battery in this situation. So like I always say, don't change anything till you get it to work. Now, it's very important that you run some type of comparator circuit, because you're not going to get a very good charge unless if you try to just put this in generator mode and just run it across the battery. It's not going to work well that way. You're not going to have any control. You're going to slow down the actual whole energizing portion of it. So you want to have something where you're building up a charge and discharging the charge and building up the charge and discharging it. And the best switch is what I said, is the capacitor discharge, the comparator circuits, and the FETs doing the switching between the negative terminal on the battery to ground. So what's happening is this high potential that's built up on this capacitor could be 30 volts. See, it's already at the plus terminal. That voltage is already there. What's missing is when it pulls the FET to ground. Then it dumps the charge from this capacitor across the whole battery. And so that's the way you really want to do it. You don't want to try to just run this kind of mode unless there's some way to regulate this across this battery. This is possible. I'm not saying this is not possible. I'm saying it is possible to charge the battery this way, but you don't have any control on what you're doing. And you're going to deplete this pretty quick if you don't have it isolated right. And you don't want to do that. So let's move on to something that does do it that way. And that would be our next drawing. Okay, so anyway, now moving on, we come to the final solution to the final machine. Something that we always wanted, something that will work for us, and something that can be demonstrated, because the whole idea was how to get a battery to recharge itself without burning very much energy here, so that we would have a power source at night, or however you wanted to use it for something that you wanted to do. And then to be able to put the charge back in the battery really quick, because it's important that you burn as little energy here to get the energy from the energizer circuitry over to this battery. Okay, so now what we're talking about is what we call a linear amplifier circuit, which allows the SSG machine to be used as a generator. So once again, we build the normal SSG, multiple stages, multiple coils, although I'm just showing the depiction of one coil to make it easy, because otherwise they need a larger piece of paper to do this. Again, we want to be in attraction mode. We want to keep the same component values as a test. 240 ohms on the base, the same transistor, 2N3055, the same diodes, 1N4007, and this little star and this little star and this little star are all the same. So they're all the same diodes. Except for what you're going to notice here is now the machine is put into generator mode by the addition of these two diodes, A and B. So what we want to do is we want to trigger this machine on, and we want this to go up and down, up and down, up and down. We want to capture both portions to charge the primary filter. Now, the reason that I'm saying this, that you must convert to use a linear amplifier regulator, a linear regulator amplifier, you must do the conversions or you will burn everything out in the circuit, because linear regulators and the associated circuits do not like to work with any static discharge or anything that's considered radiant. So you must do the conversion. So you must do the conversion from this which is the radiant spikes, which the machine is generating, which is this wave right here. Mm-hmm. But it's going fast, so it's generating a lot of these because it's multiple stages. So it's generating high potential voltages enough to charge this 15,000 pre-filter. Okay? Now, what that does is smooth this out a little bit to where you get a ripple that looks like that. So you're going from this to this. Alright? Now, to get rid of this, remember, because the linear regulators and the amplifiers want to work with a pure DC signal. So to get from this to this to this, you must have what's called a beta multiplier. Now, explanation for a beta multiplier. That takes a beta multiplier, in the terms that I'm using it in, are taking, and Zener controlled, it must be Zener controlled. I don't want to leave that out because you cannot take this over 30 volts. You don't want it going over 30 volts in this capacitor going over 30 volts because you want to stay within the ranges of the linear regulator and the amplifier. So this beta multiplier is Zener controlled. And the symbol for the Zener is this.
How do you spell Zener?
Z-E-N-E-R. Can you see that, Zener? I mean, it's kind of running together because this tip's wearing out. But anyway, so the Zener, basically in this beta multiplier, is chopping off where this capacitor can charge to, because this is charging very fast under multiple stages. And so we must arrange a network inside the beta multiplier to only allow 30 volts to go through the beta multiplier, and that's done with a Darlington transistor. And anybody that is familiar with electrical terms, because this is much more advanced than the normal SG. The normal Darlington amplifier is arranged as 2 transistors. And that's 2 N devices, NPN transistors. So this could be 2 N3055s, this could be an MJ15024s, it could be anything that will allow you to build this multiplier. So, what is a beta multiplier actually going to do? It's going to multiply this capacitance with the gain of this amplifier.
Which capacitance again?
In other words, we only have 15,000 mics
Okay.
here, and we need a much smoother filter, because coming out of this we need something that's very close, very little. This has a little ripple on it like this. I don't know if you can see that. Can you see that okay?
Yeah.
And what we want to do is we want to take this down to a pure DC level almost. So we want the gain of this to multiply the capacitance that's on this base. So we come in with a pre-filter, which the Zener controls the voltage level that the capacitor can charge to. In other words, it can only charge to 30 volts. So if I can put that there. We don't want to be over 30 volts. We just want double the battery voltage. And then what this is going to do, the output from this, right here, from the emitter, is going to feed the regulator amplifier circuit, which is this block here. The linear regulator circuit, the amplifier circuit, and the feedback circuit. Then we must monitor where this battery is. So in a way, it's a control mechanism to only allow the battery to charge to this 15 volts DC. So what we're looking at is only 15 volts for a charged battery. When the 15 volts is reached, the green indicator comes on. The feedback circuit in the linear amplifier, in the amplifier circuit, says, I can't charge anymore, and I'm going to just reduce everything to maintain 15 volts. And what will happen here is the battery will go to float, the green light will come on, the red light will go out. As long as it's under charge, the red light will stay lit. And you can put a meter on here, and so you would hook a meter right here. And you would read your voltage, and that's how you could tell if what you designed in your linear regulator amplifier circuit was working correctly, because this would only go up to 1501, 1502, 1503, but not to 16 volts, because you want to limit the machine. Once you reach this voltage level, you're charged, you're done.
So 15 volts is a good number above the standing voltage.
Yeah, you want the battery charged, you want the sulfation gone. You don't want to boil the battery away, because you're just wasting the energy in heat with this type of system. You're actually asking the SG machine, the SSG, to become a generator or an energizer all by itself, meaning and running without any drag to the machine, because you need to take power from the wheel. And this could be your fan system. So what the whole concept here, and this is where John was going the whole time, was a self-contained generator that you could use, knowing that you had a primary source, and you could use that primary source, whether it be an ultra capacitor or the new lithium iron sulfate batteries, which I'll show you here in a second of which direction this is going in. And you want to be able to maintain the whole mechanism in a small little package that can recharge your camper batteries or can recharge your house batteries, because it's quite possible. This could also be a solar input, by the way, Pat. This could also be solar input, because that's pure DC.
Okay.
And so any source could be here that was available to you to drive this machine, to build this radiant energy, to filter the energy, to run it through the multiplier circuits, and then run the linear amplifier regulator. Now, what the linear regulator amplifier is the linear regulators are quite complex circuits in that they're voltage regulators. And so the linear regulator that you must choose must be designed to run with the amplifier circuit output that you're building it on. And so I can't go into that too much, but this should be self-explanatory. There's an amplifier circuit that works just like a hi-fi amplifier in a way, where it's just emitting DC from the regulators, and the regulators controlling the whole thing. The feedback to this regulator, so it's a specialized regulator, this feedback resistor, and I'll put feedback there, must look at the battery impedance. This is how it tells when to shut the amplifiers down. It's looking at this impedance of the battery, which is going to be around 0.0022 milliohms, which is very low when this is charged. That's where the energy is going to come from. It's going to come from the battery that's charged to that level, so that you have the lowest impedance possible being delivered from that battery to supply your load for extended period of time. So, once again, as this battery goes up on the curve, from this level to this level, this level being the green state level, which means it's at 15 volts. This level means it's not charged, and this level means, so you would see red indicator light here, because this charge state is a comparator telling us where the battery is by how we set this. And I'll demonstrate that. This feedback then again is telling the regulators and the beta multiplier circuit to change the state on what the multiplier is doing for voltage into the regulators. All right, anyway, I want to make a stern point here about the way this machine works. But I'm going to give you an explanation of a flux gate by flipping this over and drawing what a flux gate actually is. So that you understand, if you really look at the machine and the concept of the machine, you'll see that it's nothing more than a flux gate that's rotating itself with its own energy that is developing from these magnetic poles. So there's 2 or 3 different types of flux gates. One could be such as this. North and south magnet, iron, non-magnetic shaft, meaning copper shaft, meaning wood shaft, meaning brass shaft, anything that's non-magnetic. Coil. So what happens is when the flux gate is in this position that you see right here, the magnetism is flowing through this circuit, just like this. So now it's just like it's one magnet with a coil of wire at this end. So it looks like the circuit's completed, and you cannot read any magnetism around the whole circuit. So it's charged. This whole thing is charged magnetically. When the situation moves to this position, the circuit's open. So that means that it just discharged itself, and now the energy appears. Because it broke the circuit, and the magnetic field now collapses, induces the current in the coil, and you get the pulse. And you would get sort of that type of situation. Positive and negative, positive and negative. At which point in time you would have to take this coil and rectify it. Well, on the SG machine, you see the diode. It's coming right off the coil. But in this case, you would put a rectifier here, a bridge. Charge the capacitor. And that would run into the linear regulator. So, here's your bridge. These are diodes. Whatever the RMS is coming out here, it would be 1.41 times more.
RMS being root mean square.
Yeah. And that would charge this capacitor. That capacitor in turn then is linear regulated with the beta multiplier, and the beta multiplier then is running into the regulator amplifier circuits, and that then is charging your battery to the state of 15 volts, at which point in time the feedback in the battery, which is back here, shows the impedance difference from battery being 0 voltage to charged voltage. Is going to show the impedance difference, going to tell the regulator to shut off. and battery's going to float at 15 volts. So that's the two machines that. So if you study this very carefully, you'll see this is nothing more than a flux gate that's rotating and generating the same signal, now in both directions. And that's being captured, controlled to a certain voltage level, multiplied times the gain on the filter of this amplifier, and then fed to the regulators. And by the way, you would also have to have a capacitor out here, because once this is filtered, then you would want to take whatever remaining was out, if there was any. And depending on this capacitor right here is how much filtering is going to be there. So if you made this big enough, within, not too big, but big enough, because it's going to multiply quickly. And then that would lead to the linear regulation amplifier, which is working just like an amplifier. It's actually switching up and down. So the regulator is very important on how this regulator works. And I want to point that out to you, that this is not a simple regulator, because it's multiple inside. And then the devices out here are devices that can handle DC. And the best thing to use out here would be transistors and not FETs. So with that, I think we'll move on to the demonstration of a linear regulator. Now that I've discussed what the circuit basically was, I'm going to show you the final machine, which is nothing more than an SG. And of course, all your magnets are around here, all north poles. Coils wound counterclockwise, you can see that. Twisted pairs for multiple circuits. So basically, this is, if you were going to contain the whole machine, it wouldn't look exactly like this, but it would contain all this circuitry. Now, next portion is the linear regulator amplifier, and as you can see from the drawing, this is the primary filter capacitor and the minus diode, which was on the diagram. And then here you can see that it's Zener controlled on the beta multiplier, which is this portion here. And if you look under here, you can see the TO3 devices, which are the transistors that make up that. And they basically can be any of the transistors from the 2N3055 family. If you come around on this side, this is this portion of the circuit is that's going to monitor the battery and change the impedance to the regulators, which are this pair of regulators and this resistor, which balances the emitter. And this is your amplifying device. And so we're going to hook it up. And of course you're seeing that you have a red light. And that red light indicates that the battery wants to charge. And so now we're hooking up the machine.
And that's the primary battery over
Yeah,
here.
that's the primary battery. All right, now, once we start the machine, it's going to become this generator, and it's going to filter, and it's going to beta multiply, and it's going to tell the dual regulator what to do in a plus or minus situation. And then the amplifier in here is going to tell the impedance, what the impedance of this battery is. So you can watch here as
So
it,
it jumped up from 83 to 92.
Yeah.
No time. Yeah.
yeah, so you can see it's charging right now. And when that battery reaches about 14.85 to 15 volts, this green light's going to come on. So it's going to come on early and then float the battery to 15. So the minute this gets its way to 14 volts,
Then the green light will start showing
the
up.
green light will start to show up, and you'll be able to see that here. It'll stay red, and green will start to come on and do this balancing situation in the regulator.
So So you got a ways to go because you're at 13.
Yeah, you
40.
remember that you only got a short time to
Yeah,
go.
yeah. But
It'll come on, what, about 14?
Well, it's going to
14
push.
something.
It's pushing pretty hard right now to bring this battery up to where its float voltage wants to be, which is at 15. Because we were drawing the battery down with this LED light, got quite hot.
yeah.
Yeah. So we don't got much to go here. I mean, if you can see that. But this is the basic function of the whole circuit that I drew on the board, and this is actually what I've been after my entire life, was to build a self-contained unit that could charge your batteries and then sense the load and put the charge into the battery while the load was running,
Nice.
which has not been done before
Right.
with the SG. So,
So at 1384, 2.
yeah, it's climbing.
How long have you been experimenting with this aspect of it then?
Well, not long with this, but it's been a constant experiment
Yeah.
since 1980s. And of course, this is all stems from the Towards a New Electromagnetics 4, which was Tom Bearden's Free Energy Motor, which was the first book that I wrote and the first motor that was actually demonstrated in Colorado Springs with Jim Watson. So see, now you're at 7.9.
9,
So it's
7,
gonna
yeah. So
climb.
it's coming into 14.
Yep, it's going to just come at 14. The minute the battery hits 14 volts,
Yeah.
it's going to shoot up like quickly.
Right.
So, we left that on for quite a while, so we drew some current out of the battery. So it's actually doing exactly what it's supposed to do right now. It's just pushing like heck with current to get that battery up there. You can hear it in the machine.
Mm-hmm.
You can basically hear it buzzing. Okay. So what it's doing right now is making sure that the amp hours are in the battery. It's going to push this current until it knows that it's going to go up,
Okay.
because basically the amplifier circuit's looking at the impedance of the battery as it lowers down to supply power, and you'll see that in a second here.
I can't see. What are we at on here?
1423.
1423, and I'm going to walk around here and get my paper towel. So what we want this battery to do is we want it to top itself off, and we want the green light to come on. And it's going to go pretty quickly now. Once it reaches halfway, it's going to go, shoot up.
So we're at 1450.
35.
35, you're right, 37, 38, 39, 40. So now it's really starting to move, right? It's starting to really put the power in there. And you can hear the machine speeding up because it's approaching its top of the battery. Now it's more than halfway. Now it's really starting to go. See it?
So at what point will the green light start coming on?
Any minute.
Well, watch.
Any sec.
Watch it. Now
There
there's
you
the
go.
balance. Now it's doing the balancing
Right.
routine where it says, I need to float the battery up to its voltage, of which it's doing right now. See, so that green light came on and said, basically your battery's charged enough to use. And then now we're going to approach 15 here, and then we're going to explain to you what's going to happen with this linear amplifier regulator.
So we're just totally green now.
Yeah, the balancing acts over it. Now it's topping the battery off. All right, see, because you're at 14.995.
Did you want this?
Yeah, in a minute, you'll just... What it's doing right now is just topping the battery. Now we can change the speed of this. You can change the speed. So let me get in here just for a second and I'll change the speed of this. See, now we just told it to go, to really push. And so now what I want to do is I want to set this battery to about 1504. See?
Uh-huh.
So battery went right up there. Machine has enough power to do that. And now if you apply the load,
Why did you do that?
just to make it move up a little bit
Okay.
faster for
Okay.
filming purposes,
Okay.
give it a little bit more current than what it had.
All right.
And that's probably how I would set it. Okay, so now you can see that this is coming down, right?
So you put a load on it.
Yeah, we put a load on it. So we need to be able to supply that load while keeping the battery in the green.
Right.
And actually, I'm trying to pull it down. And then I can add power to it if I wanted to. So you could control this device by where you set the device.
Right.
So we'll now watch the battery when I take the load off. Up, right up to 1506
It's 1482 and it went up to 1506.
immediately,
Yeah.
because the machine was supplying the load
Right.
and the battery's just floating along, not really doing anything. And if we leave it like this,
Yeah.
right, this number will increase over here,
Yeah.
but not much over 15.1, 15.2. So basically you're just topping the battery.
So it's really closed looped, isn't it?
Yes, watch. And we're going to close loop it now again, tell it to supply the load.
Yeah.
And it's going to try now to regulate and hold at 15 because it knows that's where the battery wants to be.
Yeah.
So what's running this light is the SG. And it's not touching the battery.
Right. Putting nothing out of the
So
battery.
there's a closed loop here
Right.
Yeah.
Yeah.
that's actually working the whole thing.
Yeah. Take a bow, sir.
So see, so what you have is a closed loop machine, right?
Yeah.
Basically, and you can see, okay, so if we turn this off, and you take that shield off there, Pat, you can see that that's,
It's really bright.
yeah. So in
How
a
many,
self,
how many watts is that?
that's equivalent to a 40-watt light. And look where the battery is, 1502 and climbing. So it knows the load is on it.
Right.
So now if you take the load off, Pat, which is this red wire right here, watch what the battery does.
I can't. Oh.
Okay, 15, went from 1502 to 1508.
Yeah, and see, it just knows to top the battery and leave it
Right.
there. It's just putting back what wasn't there. So yes, it's like a closed loop machine. And it's regulated to do it all. So that you must, everybody must understand that what's very important here is the understanding of servo amplifiers and how servos work. Because it looks at the impedance of this battery when you put the light on. And it knows that we changed impedance. And where we set it, we've told it that it has to keep this battery at 15. That way we're not touching the battery. What's actually running the light is the machine
Yeah.
in generator mode. So it works basically like your car, Tony, going down the road,
Yeah.
where you turn on your lights at night and the alternator's running your lights and everything that's functioning in the car and it's not touching your battery.
Yeah.
It's already topped the battery for starting the next time. So that's basically what a linear regulator amplifier can do, is these types of functions. And what it is now is the translation process from the spiked wave to the charging of the capacitor, which would be for capacitor discharging, and then moving from that to a beta multiplier amplifier, which now smooths this even more in the next filtering stage, so that none of the radiant spikes can get through to damage any of the linear circuits. The linear circuits do not like any kind of sparks or spikes or anything like that. And what's important is to balance this thing by sensing what this battery is doing right here with the comparators, and then applying the feedback to the amplifier circuit in the dual regulator.
Yeah. So I noticed you turned this little screw here.
Yeah.
You turn a screw somewhere else, is it?
Well, this screws in adjustment for the dual regulator,
Okay.
so that it can, it knows whether to go plus or minus.
Okay.
Actually,
I noticed
between
they all have
ground.
little
Yeah.
screws, don't
Yeah. Well, when you turn this screw over here, you're adjusting the
they?
comparator
Okay. Okay.
for red and green operation, and when you turn the other screw, you're adjusting two regulators at the same time. Actually, three, because you got one here and two built in. And you only need one transistor in this situation. You know, you only need one device in this situation to do this with the SG, where in the solar tracker you need two different devices. So that's basically what you have, is and this is the whole concept of the machine that's been brewing since day one. This is exactly what Tom Bedini talked about. The guy driving the motor scooter down the road using the motor, and the Energizer putting the charge back in the battery at the same time you were using it. But I wanted to break it into two things here. Primary battery and a secondary battery, so you could see what it was doing.
Right.
And it's just humming away, and it's doing work, and it's blowing air with two fans. And it also can sense that
Yeah.
you're under load. And so it's now the regulator is telling it, keep it up where it was. See?
Yeah.
Try to keep it up where it was. But it knows to stay at 15.
And the engine don't change.
No, it does not change. You
No,
just
the
hear
note
the
changed.
buzzing.
Yeah, the
Listen.
note changed.
Right.
Yeah.
What you're hearing is those spikes filling the capacitor, and then the capacitor filters that out, and then it's pure. Now, if you feel here on the beta multiplier, you can feel it's getting hot.
Yeah. Is that?
Yeah.
That's not quite yet.
Yeah. But it knows to stay there, which is kind of nice.
Yeah.
Not too many circuits can do that with an SG.
When you plug that in, the note coming out of that changed a little bit.
Yes, because of the spikes.
Right. Okay.
It has to convert more. Watch. Hear it? Now it's rattling.
Yeah.
It's
It
going,
seems to be going faster.
it's the pitch is going up.
Yeah, the pitch is going up, and there's more spikes. And what you're doing when you turn this in, see, the battery already is charged, so it's not
Right.
doing anything.
Right.
It's not going to let it go any higher. It really hasn't changed speed. It has changed pitch.
Yeah. Yeah, it feels as though it's got faster, but it's not. It's just pitch, you're right.
Yes. And so this is what the original schoolgirl motor was all about. And I was hoping within the last 20 years of me screaming about this, somebody would have figured out how to do this.
Has it been 20 years?
It's been a long time.
Yeah.
It's been since when I first started working on a concept on one of these motors was in the late 70s. Then, of course, Tom Bedini came along with Towards an Electromagnetics. I think it was in 84, Tony?
Thereabouts, yeah, 82, 84.
Yeah,
something like that.
82, 83. And I bugged the hell out of Tom Bedini. To
30 years.
explain the term. Yeah, it's 30 years. So in 30 years, whoever has been out there working on this either hasn't talked or there's never been any progress. Except for when we did it here.
Yeah. That's sad.
It's time.
Yeah.
It's time because the future is now. And
Yeah.
the next thing that's very important here is to replace this guy
Yeah.
with, and I'll be right back,
Okay. Ah.
is to replace this guy
Yeah.
with the new lithium iron phosphate battery.
Not
Sulfate battery.
ION, IRON, right?
No, iron.
Right, iron.
Lithium iron battery,
Right.
which is packing just as much wallop
Is that huge
as
thing?
that huge thing.
Yeah.
And what do you have to run it? No radiant. It has to be this
Okay.
type of amplifier circuitry to charge this. And this, by the way, charges very quickly compared to this.
So this is what? This is a
It's a regular 13 amp hour, 12 amp hour, between 10 and 12 amp hour garden battery. And this is 10 amp hours and as light as a feather and can pop, can wallop,
yeah.
can run the machine, but you cannot put the original SG output on this type of battery.
Oh, really?
Right.
So
Because
you're gonna
it
have a different way
requires
to charge this.
it requires a pure linear charger to charge this.
So is that the next one? Is that
No, the charger's already done
Okay,
for the
okay.
SG.
Yeah.
So the next thing is, when are we going to get these batteries?
Yeah. So you feel that these are the batteries of the future?
Those are the batteries of the future, the lithium iron.
Are they available?
Yes. These are what they call prismatic cells, and I'll show you a different cell here. I'll get some tape together. So anyway, that's a 3 amp hour battery, and with that I think I'm going to end this because I've said what I wanted to say
Yeah.
about the whole machine.
Congratulations, sir.
Well
Thank
done.
you.
Yeah.
End of a long journey.
Yes, it is. After many years of this.
And that concludes the story of the development of the SG motor, I guess, too. At this point in time.
Right.
Yeah.
Stay tuned.
No, thank you, John. That's great. Wow, what a difference between that I can lift up with my left hand and that I take two or
Well, you can't lift it.
Right.
We might take a short little break going in.
Yeah, and see how it works.
Yeah.
Okay, both cameras are rolling.
Oh, you want the music off?
That would be quite helpful.
Okay.
Like, yes. All right, well, the cameras are rolling.
Okay, so you're going to walk on?
Whenever you go.
Walk on. Start walking on.
Are you ready?
All right.
So I'll just walk in. Tell me when.
Go.
Okay. Returning to this
Oh, no.
drawing.
You look like you were being chased by a wild man.
I
Just
was.
walk in slowly. Don't come sprinting in.